More definitions. One-to-one. So one-to-one will feel kind of similar to what we were talking about with the definition of function. It's a function, but instead of talking about one input has to be mapped to a single output, now one output can only be mapped to a single input. So a lot of those examples that we saw at the beginning, if you want to go back and look at it, a lot of those examples were not one-to-one because we had those two outputs being mapped to, or we had an output being mapped to two separate inputs. So for this first equation, actually that might be from the first slide. I think it is. Well, we already saw it. It's a function. I have my inputs. I have three different inputs, so they can't be mapped. I can't have a single input going to two outputs. So boom, it is a function. Well, now we have to think, okay, is my function one-to-one? Well, we look at the outputs in this case. My outputs are -2, 5, and 5, so now I have repeating outputs. And my repeating outputs are mapped from two separate inputs for a -3, so this is not one-to-one. It is a function, but it's not one-to-one. Where in this case, okay, I have -2 being mapped to 1, I have 1 being mapped to 5, and so every one of my outputs only has a single input, so we're good to go. That is one-to-one. I don't know why I'm missing my hyphens there. Now there's a couple of ways to determine if a relation is a function and if it's one-to-one when looking at a graph. So if you have a graph, these are actually really nice and quick tests. And honestly, sometimes if you have a function and you're pretty good at graphing, it's not a bad idea to graph it and then use these tests to determine if it is a function or not, or if it's one-to-one or not. And so these two tests are named the vertical line test and the horizontal line test, which makes sense because one-to-one and the definition for one-to-one and the definition for function are so close to each other that the tests should be so close to each other. And how the tests work is, for vertical line test, we'll focus on that one first, is that if you can draw any vertical line that would intersect your graph in more than one spot, the graph is not a function. So these tests, you're trying to prove something is not a function. And very similar, horizontal line test, if you can draw any horizontal line in your graph and it intersects your function in more than one spot, then it is not one-to-one. So to see it in practice, this leftmost graph, I'm going to try and use the vertical line test on it. Okay, well, I drew a vertical line there. It's only hitting 1 point. One there is only hitting 1 point. One there is only hitting 1 point. I can play this game all day, but eventually you can kind of arrive at the point of saying, okay, it doesn't really matter where I put that vertical line. It's only going to hit 1 point on my graph. So it's definitely a function. Now, I'm going to determine if it's a one-to-one function. So I go through the horizontal line test, and at this point, almost like ignore those red lines. Now I'm moving on. I'm only concerned about that blue diagonal line. So I draw a horizontal line, only intersects that f of x function once. Another one, and again, I can do this all day. I will never intersect more than one, or my graph at more than 1 point, so it is one-to-one. I don't know if we can see the bottom of that, but I'll show the whole slide after. But all it's saying there is that it's one-to-one. Okay, second graph. Same type of thing. I draw a vertical line intersecting 1 point, draw another vertical line, intersects 1 point. You can play this game all day. There is no way that you can draw a vertical line that will intersect more than 1 point, so it is a function. But now let's go to the horizontal line game. So this first guy, yes, I can draw one line that would intersect 1 point on my graph. But look carefully at that definition and specifically what is underlined in that definition. This has to be true for any line you could draw. So even though I drew one line there, that's the only line I can draw that will only intersect 1 point. So as soon as I draw a different line, like right there, for example, that intersects my graph at 2 separate points. So that is not one-to-one. Last graph, same type of logic. Vertical line test, I'm trying to determine if it's a function or not. I can draw one line that would intersect 1 point. I could honestly draw another line on the other side of the circle that would intersect 1 point. But it would be very, very easy. I could give this graph to someone in 3rd grade and say, can you draw a line vertical that intersects 2 points, and they would almost do it immediately because there's so many options you can do it. So as soon as you can draw one line that intersects more than 1 point, not a function. Before we actually get into finding inverses, I'm going to have to go through a couple of definitions. And so one necessary condition in order for us to be able to actually find an inverse is a function needs to be one-to-one. So as a little bit of review, what a one-to-one function means is that any two outputs or two or more outputs does not have a single input. Or if I had a function that took x is equal to 1 and made that y is equal to 5 and x is equal to 1 and made it y is equal to 7, that is not a one-to-one function, and I cannot find the inverse of that function. All that's being said, there's going to be no question on the test that is going to try and trick you, and I'd be surprised if WebEx is going to try and trick you and give you a function and say find the inverse and then be like, oh, I got you, it wasn't one-to-one, but it is something to be aware of. Technically, in order for a function to have an inverse, it has to be one-to-one. Makes kind of sense. It'd be hard to undo when you could have two different locations to go to. And so as far as notation goes, f to the -1 of x is, and unfortunately it's almost the exact same notation as a reciprocal. If you have a function and it's to the -1 power, don't flip it over a fraction or anything like that. Instead, just know that we're actually taking the inverse of it. And a little bit more explicitly is that, again, if I have my result, if I know f of x is equal to y, then I can take my inverse, and if I plug in my end result, I should get my beginning result. And a cool little feature kind of building off of that is that if I do have a function, I can check to see if it actually is an inverse by taking the function and doing a composition of it and plugging it into its inverse, or vice versa, taking an inverse and plugging it into the original function, and I should get x as an answer. It makes sense. I had something, I got a result, and then I undid the result, so I should be at my starting point. That's a nice little way to check your answer, and usually it's not a terrible amount of work. So if you're doing a take-home exam or you have a little bit of extra time on a midterm, go ahead and plug it in, see if you get your result, knowing confidently, okay, my result was I plugged in my inverse into my function, I got an x, so I must have done the problem correctly. Wrote another note there explaining that it's not the reciprocal, so don't do that, don't do 1 over f of x, anything like that. Okay, now, a lot of talking, a lot of definitions. Really, the process is not too terrible. So your first step in the process, if you have a function f of x is equal to 2 minus the square root of x in this case, your first step anytime finding the inverse is you get rid of the f of x, you make it y. It's just going to confuse you. And they're basically equivalent. And now in the next step is really how you find an inverse. So I have my new function, and to find my inverse, I flip my y and my x. So notice how in this step, my function didn't change at all. I still have 2 minus the square root of something. All I did was take my y, put it where my x was, take my x, put it where my y was. And if you can remember that small, crucial step, well, then from there, you're just doing the same thing that we did with the literal equations. Now you're going to try and isolate y. So all we need to do at this point is get y by itself. So in this case, I subtracted 2 from both sides. I divided both sides by -1, and I square both sides, and hopefully I go, yeah, okay. I square both sides, and if I FOIL out -x plus 2 squared, I will get my final result of f inverse of x is equal to x squared minus 4x plus 4. And yes, at that point that was a y, but we know that using this kind of method of flipping our x and y's and getting our result, that we are finding an inverse, and so that is the inverse of my function. And if I wanted to, this one does take a little bit of work, but if I wanted to, I could plug this into my f of x function and I should get x back. Or I could plug f of x into this function, I would get x back. So let's see that again. We want to find the inverse of f of x, and then once we do that, we want to find the domain and range of both our original function and our new inverse function. Well, knowing from the last side, first step, pretty easy. I write the function again, except for instead of an f of x, I have a y. Now the crucial step is I'm finding the inverse, so I want to undo my function. I'm going to flip my y and my x, and then I'm just going to solve for y. So I multiply both sides by y minus 3, because it's not good to have what you're solving for in the denominator of a fraction. I'm left with y minus 3 times x is equal to 1. I distributed. I could probably divide both sides by x, but either way is fine. I distribute my x. I add 3x over. I divide both sides by x, and that is my result. If you divided x first in that step that I kind of paused on, it might look like you have a different answer. We have the same answer. It's just that maybe yours isn't quite simplified or mine isn't quite simplified. But that is my answer. That my answer is correct. The other answer you may have gotten would be 1 over x plus 3 if you did that route. Now, determining the domain and range of functions. So I don't think we've spent a whole lot of time finding range, and if we did, most likely we had to have a graph to look at or something like that. And this isn't a terrible one to graph. I mean, the inverse is kind of difficult. Let me make sure if I did. Okay, yeah. The inverse is kind of difficult. I wanted to see if I had the right notation. So that's hard to graph. That inverse is hard to graph. F of x isn't too difficult to graph, but let's just avoid graphing, and we have a neat little trick with inverses. There's a lot of neat little tricks with inverses. So in general, range is pretty difficult to find unless you have a visual, and in all honesty, even with a visual, there is kind of some sources of error you need to be wary of. But finding domain isn't too terrible. We've done it a lot of times. We have these nice 3 rules that always kind of break things down for us. And so if we can kind of use that idea or take advantage of the fact that finding the domain is easy, maybe we can do something to make it so that finding the range is also not too terrible. And spoiler alert, there is a nice way to do that. So for starters, let's find our domains. I want to find my domain of f of x. Well, I follow the same. Oh, I checked my answer first. Oh, I checked my answer first. So I'm going to check my answer first, and then I'll find my domain and range. So to check my answer, I'm going to plug in f of negative x into my original f of x function. I have this difficult fraction to deal with, but really I just subtract the denominator by getting an LCD on the lower part of the big fraction. If I did that, 1 plus 3x over x minus 3 leaves me a result of 1 over 1 minus x, which I could flip the bottom part and I get my result of x. So great job me, my inverse was correct. I got a result of x by plugging it in. Okay, now we get to find our domain. So f of x, looking at that up top, it's 1 over x minus 3. Finding my domain, I set the bottom equal to 0 and solve for x. I don't think I explicitly went through it here. I did not. So if I set the bottom equal to 0 and solve for x, I get x can't be 3. And that means x can be everything less than 3 and everything greater than 3, and that is my domain of f of x. Very similarly, looking at my inverse, 1 plus 3x over x, well, setting the bottom equal to 0, x can't be 0, so my domain is everything but 0, or negative infinity up to 0, and 0 up to infinity. Now, what we can do, our little trick or leveraging that we can use when we're dealing with inverses, is the range of my function is always the domain of my inverse, and the range of my inverse is always the domain of my original function. So I can actually use like arrows and say, oh, okay, I don't have to find the range, it's just the domain of my inverse. Boom. Domain of f of x is negative infinity to 0 and 0 to infinity, and vice versa. I don't want to find the range of my f inverse, so you don't have to. You found it with your domain in f of x. That is your range of your inverse. So if you had cool technology around, or you were really good at graphing, you could graph it and kind of find the range, where instead, in all honesty, finding the inverse in this question wasn't horrible. And once you found it, well, now you have everything. You just find the domain, and boom, you get your domain range. You get your ranges for free for f of x and f of negative x. Now, graphing inverses. I don't think we'll be graphing anything on the take-home or the midterm. Graphing inverses, there definitely will be graphing on the take-home or the midterm. But it's worth talking about. Probably will show up on WebWorks because that's just how WebWorks is. So how you graph an inverse. So looking at this picture here, I have my original function f of x. And so in order to graph an inverse, what you do is you kind of draw a dotted line, y is equal to x. That's always your dotted line. And then you treat that almost as like a mirror or a pivot point, if you will. And you take f of x and you reflect it on the opposite side of that y is equal to x line. And that's how you would graph f inverse of x. And if you had specific points, like let's look at a point on f of x. So one of my points there is, it looks like 2, 1. So 2, 1 is a point on x. If I wanted to find an individual point on the inverse, I could flip those. Okay, so it was 2, 1. If I flip them, I get 1, 2. Oh, that shows up on my green graph, f inverse of x. So if you want to be more precise about it, that's kind of the way to go about it, is to pick points on your original function, flip the point values, and then plot them on the opposite side. But as far as the concept goes, how you graph an inverse is you take the original function, you reflect it over y is equal to x, and that will be your inverse. That's it for this section.